we're going to see the energy that could be stored in a capacitor in a different way. Here we have the parallel plate capacitor, Q positive, Q negative. We have the work done, or the work, or the electrical potential energy of moving one charge here is the Q times the electric field times the distance, because this part is the force and this distance or height. So this, that is the electrical field times the height, this is the voltage. So we have that the U is equal to the voltage times the Q. If we want the total work done from moving this negative parallel plate to the distance, is the integral of this. But we know that voltage, that is the electric field times the distance, the electric field is epsilon naught, is sigma divided by epsilon naught, and epsilon and sigma, that is the surface charge density, is the charge per area. So here we have that the voltage is charge per area divided by epsilon naught times the distance. If we want to have Q divided by voltage, we have that this is area times epsilon naught divided by D, and this is what we call the capacitance. So we have that charge divided by voltage is capacitance, or that the voltage is equal to the charge divided by capacitance. So here we have that U is equal to the integral of charge divided by C, the Q, from 0 charges to Q charges. So this would be, I can put the C outside, 1 over C, and this would be 1/2 of the charge squared times C. But because we have that charge divided by capacitance is the voltage, we can also write this as 1/2 of the charge times the voltage. Or we can put the charge is capacitance times voltage. So we can also say that the electrical potential energy would be 1/2 of the capacitance times the voltage squared. So whenever of these two, the mnemonic to know when you have the voltage as just here, or voltage square, if you want to remember the formula, is here we have a capacitance, like sounds as C, of C something, look at something. So if I have the C, I can see the square of the voltage. So this is another way to think about the electrical potential energy that could be stored here. The other way is here we have a charge, another charge. We know that the electrical potential energy is the force times the distance. The force is Coulomb's constant times Q1 times Q2 divided by R squared times this R would be just R. This is U, and the K you can put it as 1 over 4B epsilon naught. Now Q1 and Q2 you can put it as you will have here a volume charge density. So the volume charge density will be the charge times divided by volume. Here it is volume. So you can put it as the total, actually this is just du, the total energy is the integral of the volume charge density, Q1 times the volume charge density of the second plate, the volume 1, the volume 2, and this divided by 4 P epsilon naught R. Now this, all this part, this and this is, is just the charge density, volume charge density times volume is just the charge, and this is divided by 4 P epsilon naught R, and this is the voltage. Actually will be the voltage of the first plate, so this is voltage 1. So we have that the electrical potential energy is equal to the integral. Actually here I forgot to put 1/2. Here is 1/2 because we are integrating the surface, the volume charge density of 1 and the volume charge density of 2, but we have superposition of them, so we are counting them double, so we need to take half of that. So it's 1/2 of the integral of the volume charge density 1 times the voltage. I will put actually voltage like this, do not confuse with the volume. Voltage 1, the volume 1.